Each day, 170 million gigawatts, over 7,000 times the power that humanity consumes, rains down on the surface, triggering a wave of activity that never ceases. The Earth's inner magnetic field steers the radiation towards the poles, triggering one of nature's most remarkable sights. The northern and the southern lights.
Well, we have to go deep into the heart of the Earth to understand that. This is a slice through the Earth. At its core, the Earth is very strange actually, because it's hotter than the surface of the Sun. So it's hotter than 6,000 degrees Celsius at the centre. But it's solid, which is odd, because you would think if you heated iron, which is what's sat at the centre of the Earth, up to 6,000 degrees, then it would melt, right? Actually, it's under incredibly high pressure, and that keeps it liquid. That makes it solid, even though it's at an incredibly high temperature, and you might think it'd be a liquid or even a gas. So it has a solid iron core. Outside that, there's this thing called the outer core, which is liquid iron, a molten iron core. And that's the key to understanding how we hold on to our atmosphere. But it's a very interesting bit of maths. It's one of Maxwell's equations called Ampere's law. So you learn at GCSE that if you have a current circulating around, just a moving electric current, you get a magnetic field, right? That's what we think, or we know, is happening inside the Earth. Because there's molten iron, you can get electric currents flowing, and that generates the magnetic field of the Earth. But this is actually the most advanced and precise equation you can write down that says that. This is a magnetic field, and it tells you exactly how that magnetic field looks when you circulate a current, which is this bit. So that just says electric current equals magnetic fields. That bit actually says also changing electric fields make magnetic fields, and I'm going to mention that a little bit later on. But basically, that says a current makes a magnetic field. That's what we think is happening inside the Earth. You get currents flowing, and that generates this force field, a magnetic field.
Hi gang! I'd previously demonstrated generating power using atmospheric electricity. A hexacopter was used to lift one end of a wire high up into the air. Meanwhile, the other end of the wire was connected to a corona motor near the ground. Electricity then flowed through the wire and corona motor, making it turn. In this video, I'm going to explain how it works. Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps, or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures. To take advantage of this atmospheric electricity, we electrically connect one end of a wire to the ground and lift the other end up into the air. In our case, we got good results at around 120 meters or 390 feet up. At 100 volts per meter or 100 volts per yard, that's 12,000 volts between that height and the ground. But just as with you standing on the ground, the wire is an electrical conductor, and so is also at ground potential. Looking at the equipotential lines around the wire, that voltage of 12,000 volts exists between some distance away from the wire and the wire. You can see that the equipotential lines are closest together at the top of the wire. This means the attraction is strongest there, and electrons make their way upward in the wire. Let's look more closely at the top of the wire. We'd put 6 sharp points using sewing pins at the top of that wire, but for ease of illustration I'll draw just one. Notice that because of the sharp shape at the point, the charges are crowded together at that point. Remember also that there are positively charged ions in the air. An electric field exists between the negative charges on the wire and the positive charges in the air. And we can represent that electric field by drawing lines between pairs of opposite charges. Notice that the electric field lines are closer together near the point, meaning the electric field is stronger there. It's strong enough to remove the negative electrons from the sharp point, where they neutralize positive ions. But due to the voltage, there are fresh positive ions moving downward and fresh negative charges coming up from the wire. We now have electricity flowing through the wire. The electric current in that electricity is very weak though. We didn't measure it, but from my experience with electrostatics, I'd estimate it in the low microamps, or more likely even lower. That's not enough to turn an electromagnetic motor, one like you use in everyday life, but it is enough to turn an electrostatic motor, like this corona motor. The corona motor consists of a plastic cylinder surrounded by sharp-edged metal blades. Every second one of those blades is connected to the wire going up into the sky. That means that when the wire starts conducting, those blades are now at whatever voltage the top of the wire is up in the sky, though opposite in polarity, positive. That's why you get a shock when you touch one of those wires. Negative charge is then pulled from the plastic cylinder through a gap between the edge of the blade and the cylinder. That leaves the cylinder with the same charge, and since like charges repel, a repulsion occurs that rotates the cylinder. The next blade is connected to earth ground and becomes negatively charged, and since opposite charges attract, it attracts the charged area of the cylinder. It then neutralizes that charged area by taking electrons from the ground. And that's how atmospheric electricity can power. What if that area was the size of the Earth? Or maybe just your neighborhood? To negatively charge such a large area would take a lot of extra electrons. Similarly, we could positively charge the area by taking electrons from it, leaving more positive protons than negative electrons. But it doesn't matter. The ground is such a large volume that the ground normally doesn't get very charged either way. It remains with a fairly neutral charge. So what's a good ground? A good ground is one that has a large enough volume that it can handle whatever charge you're trying to give it without it ever becoming very charged. We theorized about an electric fluid and chose that an excess of electric fluid would be positive and a lacking of electric fluid would be negative. To Franklin, it followed that the fluid would move from the positive area with excess fluid to the negative area that lacked fluid. It has charge on it in the area between the two plates. One plate is negatively charged and the other is positively charged. We can also draw a line between each pair of charges, representing the electric field. The closer the lines are together, the stronger the electric field. As we pull the inside plate out, the area between the two plates decreases. The negative charge on one plate moves to stay close to the positive charge on the other plate, and vice versa. That means the charge on each plate is more tightly packed together, and so the electric field lines are closer together. The electric field is stronger, and as we pull the plate out, Van de Graaff generator is a charge pump. It literally pumps charge from one end to the other. One end is a dome or partial sphere of some kind, usually on top. The other end can be a connection to earth ground, as with this one, or another dome, as in the small Van de Graaff generator I showed you, or the metal case of the motor. What's fascinating about Van de Graaff generators is that there are so many interesting things going on in them. Luckily, those things can be broken down into just a few steps. So let's start the explanation.